All right, so for the next 2 or 3 lectures, we're going to start, changing topic, and we're going to look at the properties of interactions between atoms. So we're going to see how the chemical bonds form and how we can then extend these concepts to a large number of atoms up to infinity, which is our final goal. Final goal is to understand the properties of the charge density and of the wave function of an extended system, of a crystal. So we will start by looking at examples starting from, say, pairs of atoms, where we will see the, so we'll do the test at the end, okay? So we'll start by looking at what happens when you bring 2 atoms close by. What are the possible ways in which 2 atoms interact? So let me start by refreshing some concepts of atomic physics before we get into the chemical bond. So I'm not sure exactly how much you know already about atomic physics, but let me start with something very simple. So here we have the radius. We have essentially what we're trying to describe is we have a nucleus here, which is typically of charge plus Z times E, where Z is the atomic number of the element. And then we have Z electrons surrounding this nucleus, okay, negatively charged and attracted by the nucleus. So what we typically, the way we try to solve this problem is by, what we need to solve, of course, is the interaction between these electrons and this nucleus. The nucleus itself is a point-like object, so there's no point for us in solid-state physics to understand what happens inside the nucleus. This is the realm of nuclear physics. In atomic physics or in solid-state physics, you're assuming that this is a point-like charge of given charge, and what you're interested in is the interaction of electrons with this point-like charge, positive charge. So the standard theory of atoms predicts that you have a, well, the first thing you have to discuss is the interaction of each individual electron with this nucleus. Each individual electron will see the nucleus as a point-like charge, and so there is a potential of interaction which is given by minus ZE squared over R, which is the potential seen by the electron due to the nucleus. I'm actually typically using the word both nucleus or ion interchangeably. So this is the potential of interaction between the electrons and the nucleus. Let me use N here. So this is the potential seen by an electron surrounding the nucleus at distance r from the position of the nucleus, right? I hope you all agree with this. I'm just refreshing concept that should be quite trivial to most of you. Now, this potential has well-known solutions, right? It's this is a constant divided by R, so you know the solutions of this problem. It's the hydrogenic solutions, the solutions of the hydrogen atom. I don't want to go again through the details of that solutions. What we know certainly is that there are a number of states which can be classified according to the principal quantum number n and according to the angular momentum and so on and so forth. And therefore, and that you have states which can be very deep in energy, and if they are very deep in energy, they are also very localized in space. So I'm now here showing, for example, the wave function of the 1s state, the deepest state that we have in an atom, which is typically very deep in energy and very localized in space. Depth and localization, of course, are connected to one another, right? Because the decay of the wave function of this wave function is determined by the distance of this energy level to the vacuum level. It's an exponential decay, and the exponential decay is faster, the larger is the distance between the vacuum level and the position of these states. So depth and localization are two aspects of the same physical property. So there are states that are very localized close to the nucleus, right? Close to the nucleus means that if I try to draw them here, they will be localized very close to the nucleus around here. Of course, here I'm showing the nucleus as a ball, but it's a point in my model. And then there will be states at different energies, at slightly higher energy, closer and closer to the vacuum level. And their wave functions will be, I mean, some of them will be simple exponentials like that. Some others will have nodes. Some others will have more than one node, and so on and so forth, right? I mean, I don't want to go again into the details of atomic physics. I assume that you are more or less familiar with it. I just want to extract out of this picture some elements that are important in the study of solid-state physics phenomena. The first, probably one of the most important, well, there are several important aspects, but the first one certainly is that, as we discussed already last time, there are a number of states that for us are quite irrelevant. And these are the states that I'm now highlighting only one, but with this, I mean all the states that are very deep in energy, say at the binding energy, which is, say, larger than 100 electron volts. Okay? So depth with respect to the zero. So in absolute value, this energy is larger than 100, roughly speaking, larger than 50, 60, 100 electron volts in depth from the vacuum level. Now, these states are sufficiently localized, typically, close to the nucleus, that there is no chance that these electrons can interact with their neighbors. What this means is that whether these states are in the atom or are in an atom inside the solid, that is with surrounding atoms, surrounding electrons, these states are not affected by whatever is outside. Okay? So they behave exactly in the same way whether they are in the isolated atom or whether they are in an atom inside a solid. So they're unperturbed by the presence of an environment. Now, because the study of solid-state physics is the study of how the properties of atoms change when you put them together and you form a material, these states are clearly less relevant to us, right? They don't do anything. They are useful because you remember last time we discussed their usefulness in X-ray photoemission spectroscopy, right? We use them to probe the local environment, but apart from the electrostatic shift, in fact, the electrostatic shift is probably the only property of these states that is affected by the environment. It's not that much. I mean, in terms of chemistry, it's really nothing. It doesn't really change the properties. On the contrary, states which are closer to the vacuum level, their wave functions extend sufficiently far apart from the position of the nucleus that if you start placing an atom in the vicinity now, there will be interaction between these electronic states and whatever is on the other side, or in the environment, in the environment of an atom. You have to consider that the extension of these wavelength of these wave functions is of the order of the atomic radius, right? So it's angstrom, of the order of angstroms. The typical extension of core wave functions is typically a much smaller fraction of an angstrom. And the distances between atoms are of the order of 2, 3, 4 angstroms, right? So if this is a fraction of an angstrom, the decay of the wave function is such that if you place another wave function here, there will be essentially no interaction between the core state and of an atom and the core state of another atom. On the contrary, states that are located closer to the vacuum level will have a strong interaction with their neighbors. Okay, so these states are called core states, and these states are called valence states. Actually, something interesting can be, extracted out of these considerations. If these states are irrelevant and they are very localized, and if we're only interested in valence states, suppose you are a valence state electron extended in space. What you see here, if you try to look at your core states, their spatial extension is very small, much smaller than the spatial extension of the valence states. So you can approximate their spatial extension to almost a delta function, right? Because it's much, they extend much, much less than this one. So if you are a valence electron and you look at the core states, you'll see them, you can approximate them with delta functions. But if you can approximate them with delta functions, they're going to overlap exactly with the nucleus, right? So you have a number of charges which is proportional to the number of electrons that you have in core states, which are going to be superimposed on top of the charge of the nucleus. So if you are a valence electron, the actual charge that you see, if you can get rid of core states, that is, if you can approximate it with delta functions, you can actually say that valence states see a Coulomb potential which is not that of the nucleus only, but it's given by the charge of the nucleus, that is the Z of the element, minus the number of electrons in the core. So here you have ZC core electrons. Okay, so if you have a given number of electrons that I can approximate to be in the core, of course, there will be ZV electrons in the valence, and of course, ZV plus ZC must be the atomic number, right? I partition my electrons into core states and valence states, and I assume I'm a valence state, and I look at the core states, and the core states are delta functions, but if they're delta functions, they overlap with the nucleus, and they're indistinguishable with respect to the nucleus, right? I see a point charge given by the nucleus of charge Z, and I see point charges, ZC point charges with opposite sign located at the nuclear position. So the overall charge seen by valence electrons is given by this number. Okay? But because of this, Z minus ZC, of course, is ZV. Okay? So this is the effective nuclear charge seen by valence electrons. Okay? I guess this is probably obvious to a number of you, right? But let me just refresh some of these concepts. So valence electrons, in the approximation that core states can be approximated by delta functions, see a charge due to whatever is located in this position, which means the nucleus plus the core electrons, see a charge that is given by the number of valence electrons times the electronic charge. So this way we have essentially removed completely the core states. The core states, as at this point, we can forget about them. We can just concentrate on valence electrons and assume that these valence electrons are attracted by a point charge with charge ZV times E. Now, there's something else we are forgetting at this point, and this is the interaction of the electrons with themselves, the valence electrons with themselves. I'm still reasoning in terms of a single atom, right? I'm not yet introducing the presence of other atoms. I'm just reasoning in terms of how can I determine, for example, the wave functions of the valence wave functions? I've made an important approximation. That is, if I determine the valence wave functions, I can remove the core states and replace them with an effective charge which takes into account the presence of a nuclear charge plus the core states, which is the first statement I can make. But then, when I want to determine the wave functions of the valence electrons, I need to consider that in addition to the interaction with the nucleus, which I've considered, right, Z E squared, in addition to the interaction with the core states, which I've considered when I say that, look, the real interaction with the point charge at the center is not Z, but it's ZV, because there's also the core states. In addition to that, there is also interaction of electrons, valence electrons, with themselves. So if I am a valence electron, the Hamiltonian that I will have to obey is an Hamiltonian in which I have roughly plus the electron interaction, the electron-electron interactions between valence electrons. Between valence electrons. Let me clearly put an approximation here, because I've made a number of approximations in saying this, right? I've approximated the core states to point charges. What else? Well, implicitly I've made another approximation, which is not, which is quite strong, in fact. And in fact, I need to always keep in mind that when I do this exercise of removing the core states, there is not only the charge that these electrons see due to the presence of core states, but there's also the fact that these states must be orthogonal to the core states, to the underlying core states, right? Because they are the result of the same Hamiltonian. So if I remove some states at the bottom, one thing is to say that I have to consider just the interaction, the charge, the electrostatic interaction with these states. But I also have to consider that these wave functions, they all must be orthogonal to all the core wave functions because they are the result of the same Hamiltonian. So somehow this has to be reflected in the valence states. Now, it is important. Orthogonality with the core states is important and must be considered. However, if I continue assuming that these core states are localized very close to the nucleus, clearly orthogonality will affect only the wave function close to the nucleus, right? Because this is where the wave functions have to, have to do whatever they can to orthogonalize to the core states. Outside this region, there is no overlap. So if I want my wave functions to be orthogonal to this one, I need to modify essentially only the region very close to the nucleus, which is where there is overlap between these two. Right? Orthogonal means that when I take the expectation value of their product, these two wave functions, the product of these two wave functions gives me 0 in terms of expectation value, right? So if this wave function is non-zero only close to the nucleus, I need to somehow modify my valence wave functions in such a way that their overlap with this function gives me 0 when I integrate it, but that is only relevant close to the nucleus. If I go outside, if I go here, this wave function is already 0, so I don't need to do anything outside the region very close to the nucleus if I want to make these functions orthogonal to the core states. So once again, I'm going to modify my wave functions only very close to the nucleus. So this affects my wave function only very close to the nucleus if I want to make them orthogonal to the... So once again, I'm making a number of approximations, and I would like you to keep them in mind, but I need to simplify my life, and so I want to get to the end with some at least qualitative knowledge of what I should expect for the Hamiltonian that controls the behavior of the valence states. And within all these approximations, we can probably say that there's, of course, the kinetic energy. There is an interaction with something which contains both the nucleus and the core states, and this takes the form of ZV as a Coulomb potential, approximately, right? It's not exactly, because this is not exactly a delta function, but approximately like that. And then what I cannot forget is the fact that even electrons themselves, the valence electrons themselves, interact with each other. Now, this in principle is an Hamiltonian up to this point, an Hamiltonian that you know very well how to solve. Right? It's just a standard hydrogen atom Hamiltonian where you have here a coefficient which is not just, say, for the hydrogen atom this would be 1, ZV would be 1, otherwise it's a number. I mean, you know how to solve this Hamiltonian. So what really the complexity comes into play is when you start introducing interactions between electrons. This is a very difficult topic in solid-state physics as well as in atomic physics. I don't know how much you have seen already about many-body quantum mechanics. Probably nothing, right? I guess so far you've only seen in your life the quantum mechanics of single particles, independent particles. Has anybody of you already seen some concepts in so-called many-body quantum physics or not?
I don't know, but I saw something free, bond-free, and interaction.
Interaction between?
Yeah. Okay, we have electrons.
Okay.
The interaction can be free, bond-free, or bond-bond.
Okay, this is a very specific example of a many-body. Let me just give you a flavor of why this field is so difficult. And also, I'll give you also a flavor of how modern solid-state and atomic physics deal with this problem. It's still an unsolved problem, by the way. It's one of probably of the most important and open problems in fundamental physics today. So when I write this, I'm already writing something completely wrong, I mean, formally. Because what do I mean by this if I have more than one electron? If I have an electron, this is clearly the kinetic energy, I mean, the gradient of the wave function with respect to the position of that particular electron, right? This is what we mean by momentum, by kinetic energy. What we mean by this is the distance of that particular electron to the nucleus. But here we are introducing interaction between electrons, right? So I need to explicitly introduce the presence of other electrons, of more than one electron. So here I need to play, let me assume that I'm not just playing with one electron, but I'm playing with two electrons. Just to, I mean, one step further with respect to what is your, I mean, a field you know very well, which is the behavior of a single particle. Now we have two particles, right? But if you have two particles, this is not the correct way already. I mean, this is really something that I wrote down qualitatively. The real Hamiltonian of a two-particle system is an Hamiltonian that must contain both variables, right? So it will contain the gradient of the wave function with respect to particle 1, right? That would be the gradient with respect to this coordinate. Then there will be the gradient with respect to the other coordinate, coordinate 2. Then there will be the interaction with between particle 1 and the nucleus. Then there will be the interaction between particle 2 and the nucleus. And then there will be a repulsion between the two electrons. Right? So if I want to be precise, what I should write in principle, if I have two electrons, is not something like that. I mean, something like this doesn't make any sense, because this is the Hamiltonian of a single particle which is interacting with other particles. But that's not the way in which I should consider writing my Hamiltonians. If I have two relevant quantum particles, I need to write down the full Hamiltonian of the two particles in principle together. Now, clearly there are pieces like this plus this, which of course correspond to the Hamiltonian of particle 1 in this field. Similarly, I have this piece and this piece here, which are the Hamiltonian of particle 2 in the field of the nucleus. But as soon as I introduce the interaction between 1 and 2, I cannot decouple these two Hamiltonians any longer. If this was absent, if there was no interaction, I could write this total Hamiltonian into a sum of two completely independent Hamiltonians. So I could have in principle solved the problem as independent problems. If there is no interaction between two pieces between two Hamiltonians, there are no terms in common, the two Hamiltonians are completely independent. They don't feel each other. The two particles don't feel each other, and you can solve them independently. But here you have an interaction. And so you cannot decouple Hamiltonian 1 and Hamiltonian 2, because the two particles are interacting with one another. Another consequence of this is that this Hamiltonian is defined now in a 6-dimensional space, because I have two particles, 3 degrees of freedom per particle. So this Hamiltonian depends on 6 independent degrees of freedom. And of course, if you want to solve this Hamiltonian, the wave function will be a function of 6 degrees of freedom, not 3 only, because it's an Hamiltonian that depends on 6 degrees of freedom. So the solution of this Hamiltonian will be a wave function of R1 and R2, right? So 3 plus 3, 6 degrees of freedom. Now, suppose instead of having 2, I have 3 particles. If I have 3 particles, then I will have delta 3, I will have 1 over R3, and then here I will have 2 more terms, R1 with R3 and R2 with R3. And the wave function will be a function of 9 variables, right? So this wave function is defined in R6, right? This one. The Hamiltonian for 9 particles is defined in R9. Let me take a single, say, carbon atom. Carbon is a very light element, so there's not so many electrons. So in carbon, there are 6 electrons. Okay, so let me take carbon. What is the wave function? Where is the wave function of the electronic state of carbon? In which space? Let me assume that I don't consider the distinction between core and valence, okay? That I work with all 6 electrons. Well, it will be a wave function defined by 6 by 6 degrees of 6 times 3 degrees of freedom, right? So this one will be defined in R18, right? Iron, 27. R to the 81, right? Okay. Yes?
What about interaction spin?
Oh, that's a good point. I'm not going to discuss spin here. This is only going to complicate my discussion. Yes, I mean, spin is important, and spin actually determines a number of properties that your wave function, spatial wave function, has to obey. But let me keep that for a different course. This course on, say, quantum mechanics, many-body quantum mechanics. It is there, and it is important, but let me, for the time being, otherwise, Again, if I start discussing also the spin variable, there would be no end. But spin is important, yes. The answer is that spin is important. And spin, for example, determines the symmetry of this wave function, as you might already know. I don't know whether you know whether symmetric or antisymmetric wave functions. But allow me not to enter into these details, because these details only complicate my discussion for the time being. I just want to make a simpler argument. Even if you forget about spin, then the argument I'm trying to make is that these wave functions are going to be defining spaces which, even for a simple iron atom, are to the 81 dimensions. I think it's 27, but anyway, something of that order. Okay, now suppose you are a physicist that wants to solve this problem, and you try to do it first analytically. Try to solve this Hamiltonian for 3, 4, 5, 6, 27 electrons. You want to solve atomic physics problem. And you try to do it with some analytical tools. Well, I can guarantee that there's no analytical solution of this Hamiltonian, let's say, beyond two electrons, beyond 2 electrons. Okay, so any atom of periodic table, with the exception of hydrogen and helium, but even helium, it's not really exact. There's no way you can come out with an exact analytical solution of this problem, which is defined in R6 for helium, for example, right? 2 electrons. You go to to any other element in the periodic table, you'll immediately find yourself in an extremely complicated problem with no analytical solution. Okay, but we're all very good at playing with computers, right? So why not, trying to solve it on a computer? After all, this is second-order differential equation. There are several tools available to solve the second-order differential equation. Why don't we try and just solve it on a computer? All right, we need to solve a second-order differential equation defined in some space. Well, let's take carbon, R to the 18. We're trying to solve a second-order differential equation in a space of 18 dimensions. When you deal with numerical solutions, what you typically do in practice is to express your wave functions in a discretized set of points. Suppose you are in 1 dimension, right? In 1 dimension, you want to find a wave function in this particular space, and you want to solve your Schrödinger equation. The way you do it, you just discretize your space, and you solve your wave functions by discrete points, right? By finite differences, typically. So the most obvious thing you have to do is to define your wave function in all these points, in 1 dimension, right? Here, this is 1D, so we are in R1. Well, how many? Depending on the complexity, you may wish to consider a number of points, which is 100, 1,000, but depending on the complexity of the wave functions, right? If your wave function is a very simple one, probably 10 points are enough. If it starts having many wiggles, you need 100 points, perhaps. So what you need to do is to store in your computer 10, 100, 1,000 real numbers, the values of your wave function at those points. All right? That's the standard way to solve a second-order differential equation. Fine. Let me go to R2 now. I'm not yet at the hydrogen atom. The hydrogen atom is R3, by the way. So let me go to R2. How do I do it now? It's a function of 2 variables in space. Well, then I just extended to a 2-dimensional space, right? I discretize my space. I construct a grid. Right? And here again, I need to decide again, how many grid points do I want to work with? If I were using 100 here, I need 100 probably also in the other direction. How many points will I have to be working with? 10,000, right? Or, if you wish, 100 to the dimension of the system. Fine, 10,000 is okay. 10,000 real numbers. Any computer, even probably my Android, my cellular phone, can handle 10,000 real numbers. Notice that we're only discussing, how to keep in memory the function. We are not yet discussing how to solve this equation. We're just discussing here how to store in the memory of my computer the value of the wave function. All right, let me go to 3 dimensions now. 3 dimensions, if I need 100 points in one dimension, 100 points in the other, I have a cube of side 100. So therefore, in R3, I will need perhaps 1,000,000 points, right? 10 to the 6. Let me go to carbon. How many points do you need to describe carbon properly? If you assume that you need 100 points in this direction at least. 10 to the 18. I mean, if you deal with carbon, right? Or 36 points. So you need to store in your computer 10 to the 36 real numbers just to store the wave function. We're not yet even started with trying to solve the problem. No computer in the Earth would be able to store. There's no storage place that will allow you to store 10 to the 36 real numbers. And big database with big anything hard disk will allow you to store 10 to the 36 real numbers. Just storing the value of the wave function, not yet even trying to solve the problem. I mean, imagine iron. Imagine a solid, a molecule, which is made of 100 electrons, right? So you're not just dealing with 18, but you're dealing with 300 degrees of freedom. Conclusion of this, the many-body problem in physics is an extremely complicated problem, an extremely complex problem, because the wave function is expressed in a space which is huge, which is just huge. And it's impossible even just store the value of the wave function in such a large space, even for a system made of a single atom, of a simple element like carbon. So we need to come out with solutions here to approximations, because this is growing so fast, exponentially so fast, that even if we say, even saying, okay, I'm unable now, but perhaps in 2 years I'll be able to do it. No way. I mean, 10 to the 36 real numbers, probably not even in 10 or 20 years we'll be able to store them on a computer. Okay? So it's growing so fast that there's nothing we can even say from the technological point of view. Computers are not growing that fast to allow us to say that in a few years we'll be able perhaps to solve it. We need to find solutions to this problem, or at least approximations, good approximations to this problem. There is, of course, this is a huge field of research, as I was telling you before. It's probably one of the most active fields of research in physics, the field of many-body quantum systems. But there has been, in the history of physics, one breakthrough, which I would like to describe for you in a few minutes, of course, just qualitatively, which is a statement that was a theorem that was proved in the 60s, that gave the Nobel Prize to the person who actually came out with this theorem. The person is Walter Kohn, and he got the Nobel Prize very late, actually, 35 years after in chemistry, got the Nobel Prize in chemistry, after the theory was first proven. So what he essentially proved is that you can indeed, I'm now stating the theorem in a very simplified, and people who actually know the theory might be criticizing what I'm saying, but I'm going to oversimplify this statement. He actually said that there is a way in which you can write your Hamiltonian for an arbitrarily large number of electrons that is essentially made of a collection of independent Hamiltonians of this kind, where here you have, so suppose this is particle 1, for example, R1, R1. Of course, in principle, the electron interaction depends on R1 as well as on all the other variables, right? So this would be the exact statement. The Hamiltonian contains this particle as well as all the other ones. The theorem states the following. You can remove all this and replace it with the total charge density of the electrons at point R. So in other words, or R1, sorry, R1, because that's the position of the particle. So in other words, you can not really approximate, you can express exactly this potential, which is in principle a function of all the other electrons. You can express all this in an effective way by replacing all the other positions with the density, the electronic density at the point where your particle is. Of course, the electronic density will contain information about all the other electrons, right? Because the density is composed by all electrons. So the total density of the system is made up of all the electrons that I have in my system. So some information is retained. But I don't need to retain all the information about where all the other electrons are. I just need to keep information about the overall density of the system. That is, I only need to know where the global charge is. I don't need to recognize inside the global charge whether this is contributed by electron 2, 3, 4, or whatever. I just look at the global charge. So that's the total charge density. So this theorem, it's a theorem, so it is exact, and it states that I can write this Hamiltonian as a collection of independent Hamiltonians, that is, for each particle 1, 2, 3, I can write exactly the same, with 1, 1, 1 here, and the density at point 1. There is only one little problem. We don't know what this function is when I replace it with rho. We just don't know. The theorem states that this function exists, and it's one, and it's unique. It exists. It's somewhere there. I mean, it's somewhere. But we don't know the shape. We don't know what this function is. And nobody knows what this function is. Not yet, at least. Okay? So it's an extremely powerful theorem because it allows us, in principle, to work with independent particles, 3 degrees of freedom at a time, not 18 degrees of freedom altogether. 3 degrees of freedom at a time. Unfortunately, the theorem, only states that this function exists. It doesn't tell us the shape, what this function is. It tells us that it exists and it's unique. There's only one function. But it doesn't tell us the shape of this function. So here is where all the approximations start to be introduced. People have started to introduce approximations to this function, or at least have started to work with functions which give results which are meaningful, but we don't know what the real function is. It's a very, it's a very, very, very intense field of study, the one that is trying to figure out what this function could be. By the way, all this goes in the name of density functional theory. Okay, and this theory is the theory that states that the function or functional, because this is a function of a function, right? So it's actually called, mathematically speaking, it should be called a functional, not a function. So that's why it takes the name of functional. In density, because it's a functional of the density, of the total charge density, or DFT. People also call it DFT. If you have a guess for this wave function, I'm sure you're going to get the Nobel Prize if you find that function. No, for sure, I mean, because if the person that just proved that function exists, that functional exists, got the Nobel Prize, I mean, can you imagine if you actually find it, what the functional is? Okay. So I just wanted to give you very qualitative facts about the many-body quantum problem and to show you that this is a very important problem, a very deep problem, a very complicated problem. It's full of mathematics. It's full of numerics because there are, of course, clever ways to handle functions in 18 or 27 or 80 dimensions. I mean, it's not just the example I've shown you is really brute force, discretizing the space in a grid and things like that. So there's a lot of work that people are doing to try and solve this Hamiltonian exactly without having to invoke this theorem since we don't know the exact function that satisfies that theorem. All right, so what time is it? Yes, okay, so we still have about 15, 20 minutes to... that was a sort of digression into many-body quantum physics. Let me go back now to my original problem. And my original problem was after I discussed atomic physics, after I discussed core electrons, valence electrons, and I discussed how I determined those wave functions, the challenges related to the fact that I need to consider electron-electron interactions explicitly. Suppose I've gone through all this exercise and I've a good estimate of what is the energy, the wave functions, and the properties of an atom. Okay? So you have an atom here with a given charge and with a given charge density around. So some electrons here that are, for which I know the shape because I've been able to solve all the problems that I discussed at the blackboard there. Okay, so that's an atom. Let me now bring another atom close by. I take another atom and I start bringing that atom closer and closer. That's exactly what we want to understand, right? The formation of a chemical bond, the formation of solids, and so on and so forth. And let me start with a pair of atoms. What's going to happen to this system when I'm approaching the two atoms? Well, there are a number of things that will happen, that may happen. There are electrons here, there are electrons here, there is a nucleus here, there is a nucleus here. The first obvious thing is that these electrons will be somehow affected by the presence of both this electronic distribution and by the presence of the nucleus. Electrostatic tells us that, well, the two electronic clouds will repel. This electronic cloud will be attracted by the nucleus, and this electronic cloud will be attracted by this nucleus, right? Of course, the electronic attraction of this electronic cloud with this nucleus is already taken into account because this problem has been already solved. So the shape of this wave function reflects precisely the interaction of these electrons with this nucleus. So what I need to consider is only the interaction as an additional ingredient is only the interaction of this electronic cloud with this nucleus, this electronic cloud with this nucleus, and this electronic cloud with its neighbors. So when I start, having these two approaching, there will be some charge redistribution, right? That is a consequence of this interaction. Now, electrostatics is not the only theory that we need to consider. There is also quantum mechanics, right? Electrons will start feeling this point not just around electrostatic classical objects, but there will be an attraction because, well, there will be an interaction because these electrons will start feeling the potential due to this nucleus in a quantum mechanical way. Right? So there are a number of things that may happen when I bring two atoms together. Now, the way we classify the possible consequences of bringing two atoms close to one another I mean, it's typically borrowed from chemistry, from concepts elaborated in chemistry. There is, of course, I'm now going to classify the possible phenomenology, but of course what you have to keep in mind is that this is only a classification that holds only in extreme cases. The truth, when you take an arbitrary element and you bring it close to another arbitrary element, is that something will happen and it will be a little bit of everything that I'm going to describe. However, for the purpose of at least clarifying what are the fundamental aspects, the possibility, the extreme cases that can happen when I bring two atoms in interaction, it's worth considering a number of cases, that typically 4 or 5 cases, which happen to be quite common or regular among solids. Okay. So the first case is the case in which there is a covalent bond formed. We are going to discuss this in quite some detail next time, but let me just describe it very qualitatively at this stage. So a covalent bond typically takes place between atoms that are very similar. If the two atoms are identical, for example, take two hydrogen atoms, right? Single proton, single electron, single proton, single electron on the other side. If I start bringing them close to one another, what's going to happen is that the charge distribution on the right and on the left, we will see it next time, they will start to move, this one in this direction, and this one in this direction, and eventually they will start accumulating charge in the middle. Okay, so the two charge distribution, electronic charge distributions, will move this one because it will be attracted by this nucleus, and this one because it will be attracted by this nucleus, primarily. You shouldn't forget that there is also repulsion due to the presence of the two electrons, but the result of this will be a slight accumulation of charge in the region between the two atoms. And of course, in the process of doing this, the energy will be minimized, will be lowered with respect to the energy that the two systems, the two atoms had at the beginning. Okay? So the covalent bond typically corresponds to a redistribution of the charge and to an accumulation of charge. Between nuclei, and of course, as a consequence of this, you have a reduction of the energy of the system. The energy of the system goes down. And typically this takes place between like atoms. You may also have, in case we are talking about completely different atoms, for example, atoms lying at the opposite side of the periodic table. The typical example is sodium and chlorine. You may have that electrons in one atom prefer to jump on the other side completely, just because the attraction due to this nucleus is much stronger than the attraction they originally had while staying in their original atom. Okay, so you may have not only a redistribution of charge that accumulates charge in the center, but you may have a complete transfer of charge from one atom to the other one in formation of two ions. The typical example, again, is sodium chloride. And this is what we call the ionic bond. Right? So this is really example sodium chloride. Right? Sodium chloride, the two atoms, sodium transfers an electron to chlorine, which becomes charged, negatively charged, and sodium becomes positively charged. And this is really a transfer of 1, 2, 3 or something electrons from one atom to another. Now the consequence, of course, of this is that, the energy has to go down. The energy in these processes always goes down if they happen, right? Otherwise, they wouldn't happen. But in addition here, you have also the electrostatic energy of interaction due to the fact that these are oppositely charged Coulomb ions. So generally speaking, the ionic bond also gives rise to a lowering of the energy. By the way, in terms of what is the value of the energy gain by forming these bonds, we're typically talking about, here, we're talking about 2, 3 electron volts, and something also similar here, 2, 3 electron volts, probably a bit less here, 1, 2 electron volts in the case of the ionic bond, per pair of atoms. So these are the two extreme cases where either the charge is accumulated between the two atoms or where the charge is transferred from one atom to the other one in the case of ionic bonds. There are, of course, other ways in which the atoms bind to one another, and I'm just going here to list some of the weaker bonds that can be classified, at least in chemistry. The van der Waals bond is a bond in which there is almost no charge redistribution, but it's what results from the interaction between two neutral and unperturbed charge distributions. And this is typically the bond that results when you have atoms, either you have atoms that are very far apart, neutral atoms very far apart, in which this charge organization cannot take place because they are very far from one another, far on the atomic scale, or between atoms that are extremely inert, like noble gases. Noble gases don't like to move their charge around. They remain neutral, whatever you do. And so the kind of interaction that they have is this so-called van der Waals interaction. Okay, so this is a weak interaction, not weak in the sense that it's a weak force. It's weak in the sense that it's weak. It's weaker than the other ones. Between neutral it's actually in general, neutral charge densities, particularly at large distances. Here the charge is not, there's no redistribution of charge. It's simply the interaction between two neutral objects at large distances. Now, you may argue that if you have two neutral objects at large distances, there is no interaction, right? Because there is no electrostatic interaction. This is not entirely true, because even at large distances, there will be a small perturbation of the charge of this atom, well, due to the fact that the other atom is not just a neutral object. There is an internal structure in the charge density of the other atom. So there is a little bit of charge distribution on the other side. And similarly, if you sit on the other atom, you see this atom with some charge distribution. In addition to that, there are quantum fluctuations that give rise to the fluctuation of the charge on the other side that, if they are correlated to the quantum fluctuation on this side, they can give rise to a weak interaction between neutral objects located at large distances. It's a complicated theory, and again, I don't want to enter into the details of that, but I think you should know that this kind of bonds exist. And in fact, these kind of bonds are very important because these are the bonds that probably control most of our macroscopic world, these ones here. If I take with my finger and I push this chair, right, I'm not going to create covalent bonds, nor ionic bonds, right? I'm not certainly going to create these bonds. Yet the chair is moving, so I'm interacting with the chair, right? So how do my atoms in the tip of my finger interact with the chair is through forces which are very long range in nature. Because nowhere the atoms that compose my finger will get close enough to the atoms that compose the chair to form covalent bonds. If that happened, by the way, I would just stick to the chair and I wouldn't move, of course, right? So most of the macroscopic phenomena are actually driven by van der Waals bonds, because this is the bonds that you form when you essentially try to move and play with macroscopic objects without forming real. Clearly, the atoms inside this piece of plastics or here, they are tied together by covalent bonds, right? And that's a very stable kind of bond. But the bonds between two chalks, when they hit, when they touch, this is van der Waals bonds. They never get close enough that the atoms of one chalk to the other one to form a real chemical bond. They stick. They stick together only because of van der Waals. In fact, there is from a technological point of view, it's very interesting to develop materials which show strong van der Waals bonds, which looks like something strange, right? Because these are weak bonds and you want to make them stronger. Why do you want to do so? You want to create materials, well, glues, in fact. Glues are an excellent example of that. Glues don't form chemical bonds, but they form a special class of van der Waals bonds which is very strong, right? So when people developing glues, for example, they are doing research and trying to develop materials that make these bonds as strong as possible without, of course, forming chemical bonds, real chemical bonds, with a few exceptions. There are glues that form real chemical bonds, but the majority of them are just forming strong van der Waals bonds. And then there is another class of bonds which is very, very, very common, particularly in biological systems, and this is the so-called hydrogen bond. The hydrogen bond is a bond that is very peculiar. It's, yes? Oh, van der Waals bonds, it can be typically of the order of less than 0.5 electron volts, let's say. Probably even less than that, 0.1. Again, there is no clear distinction between what is what, but typically these bonds are typically less than 0.1 electron volts per pair of atoms, of course. Per pair of atoms, right? So if you form a bond between a macroscopic objects, the energy that you are playing with is much larger, of course, because you have to multiply times the number of. The hydrogen bond is a bit stronger. It's about 2.5 electron volts. And it's a very peculiar kind of bond. The hydrogen bond is the bond that forms when you have oxygen, perhaps in a water molecule, with another oxygen. This is really the most common example of a hydrogen bond. It's a kind of ionic bond in some sense, although there is no charge transfer. It's ionic because in the water molecule you have negative charge on the oxygen, positive charge on the hydrogen. So the water molecule itself is likely, actually, it is a primarily ionic bond within the molecule. And so if you have a negative charge on the oxygen, there is an electrostatic attraction between the H and the O. Okay? Because these are oppositely charged. So this is the main source of attraction, for example, in liquid water. Liquid water is liquid and sticks together. The molecules stick together because of this electrostatic attraction between the hydrogen and the oxygen. And this typically goes in the name of hydrogen bond. In fact, almost all biological objects stick together and are form compact objects because of these hydrogen bonds. Take your DNA, for example, but in fact any protein. They take those conformations because of the formation of hydrogen bonds between different parts of the molecule. Okay, so it's really an electrostatic interaction between an hydrogen and a negatively charged ion on another side. So there's no chemical bond here. This bond is weak, so it can be broken very easily. In fact, in liquid water, when the molecules move around in the liquid, this bond is broken and formed, continuously, right? Because when the molecules diffuse in the liquid, they continuously form these bonds and then break them and reform them with another molecule and so on and so forth, so that diffusion can take place. So liquid water is condensed. It's not just a vapor. It's a condensed system because of these bonds, but these are weak enough that they can form and break easily in the fluid form. Yes?
Can we make a distinction based on length scale that, for instance, at what length scale is van der Waals bond to become more replace more?
Okay, well, the typical bond lengths are of the order of 4 or 5 angstroms. So the distance must be larger than 4 or 5 angstroms, which is larger, of course, than the distances that describe the covalent bond and the ionic bond, which is a few angstroms, 2, 1, 2, 3 angstroms.
So for covalent and for ionic, almost is it the same?
Yeah, it is also almost the same, of the order of a small, 1, 2, 3 angstroms, depending on the system. Yeah.
What about the hydrogen bond?
Hydrogen bond is, this is about 2 angstroms, roughly. So it's quite short, but the strength is not that much because there is no charge transfer. So there's no real chemistry. It's pure electrostatics. This oxygen is preventing from moving its electrons because these electrons are stuck by the 2 positive charges on the other side that keep them close to the oxygen. So there's very little chance for those electrons to move. So it's pure electrostatics, yet the distance can be quite short, comparable to a covalent bond. Well, this is a real covalent bond or ionic bond, and it's 1 angstrom, for example. You have to consider that the proton, the hydrogen atom, is also very, very small. So you can get very close to oxygen. So in this particular case, you have a covalent bond, 1 angstrom, and a hydrogen bond, which is 2 angstroms.
Okay, in the physical world, how much is, which one is dominant in percentage? Is ionic or?
In dominant, so you're asking what is dominant among these bonds? It depends what you're interested in. If you look at about the total binding energy, clearly the covalent bond is much stronger. So the amount of energy you gain in forming water is dominated by the energy due to the formation of the hydrogen of the water molecule. Okay, but once the water molecule is formed, it's not going to break. So if you're interested in phenomena like, say, diffusion, the properties of liquid water, who cares about the covalent bond here? This is just like a stick. It's rigid. It's there forever. What is important for you to understand is the hydrogen bond if you want to understand how much water diffuses, what are the properties, the physical properties of water. So it really depends on what. So covalent bond is dominant in terms of energy, but it's rigid. The hydrogen bond, because it is weaker, it is more dynamic, and therefore it's what determines the physical properties of the system.
Yeah, not specifically hydrogen bond, but those.
Yes.
I think van der Waals will be dominant. I hope so. I don't know.
No. This actually. Oh, you mean in general, overall?
Yeah.
Again, it depends. If you want to understand, how you can break this piece of material, then you have to ask yourself how much energy you need to break the covalent bond. If you want to understand how much energy you need to move it, then of course it's the van der Waals bond. So it really depends what you're interested in, I guess. Okay, I would like to stop here if possible, unless there is an urgent question. No? Fine.